All right. So welcome everybody. I was just mentioning that I'm usually available to stay until 10:30 p.m. Sometimes I have to go around 10 or so, but I try to stay until 10:30 p.m. But I try to stay as long after class as I can. All right. Anyway, so where are we? First of all, as I said in my email, I thought I had to email this. The month of September is going to be very tough for me. You can all say "aw," simply because, well, especially these weeks, because I'm still doing new videos for chapters 1 and 2. So that's going to make grading very slow. So I'll do what I can. I hope I can get these two done in a reasonable amount of time. Okay, but bear in mind that once we start here, I can start using my videos from spring, and that'll really open up time for grading. I hope that I won't have to postpone this till October. I'm going to try to grade these things in September, right? But October would be much more open for grading. That's for sure. Okay, I started chapter 1 last week. We're going to finish chapter 1 this week in terms of the lecture. So keep working on that homework, all right? I'll start chapter 2 next Tuesday so that we're on track, although chapter 2 will not be due on the chapter 1 homework, of course, all right? And we'll have a homework session in the last part of Tuesday of next week. And also on Thursday, we'll have more time for the homework, and I'll continue with chapter 2. And then the chapter 1 homework is due Friday of next week, Friday 9/18, end of the day. That's when the chapter 1 homework is due. Now, will I get the chapter 0 homework done by then? I hope so, but please understand that these videos, I'm proud of their quality, but they take a lot of time. All right, so I'm doing my best. All right, but the chapter 1 homework is due by Friday of next week. All right. Okay, any general questions about the schedule? Okay, I hope you all had a good holiday weekend, yes? All right, any questions about the schedule?
Sorry, my the voiceover was not on, but did you say what skim 1.11 means?
Oh, skim 1.11. Okay, 1.11 is actually a calculus section on derivatives. So there is no homework, no required homework for 1.11. Okay, basically I'm taking the ideas of 1.10, extending them to calculus. So 1.11 is not required homework.
Okay, thank you.
Yeah, there are 3 short problems. I encourage you to look at them, but 1.11 is not required. And anything that's labeled additional problems, you don't have to do. That's just for your extra learning, which is nice. We can talk about it. All right. Any other questions before we start? Any other questions before we start? You can also chat. All right. Also, student to student is fine. You know, you chatting to the class. Although I'd like to keep it kind of on topic. So I think if there's too much on the homework questions, I think we might overload the chat. So let's try to keep the homework questions for after class. All right. I can usually stay half an hour to an hour. Any questions before we start? I am recording. Yes, I'm recording. I'm recording. Okay. So you can keep chatting. All right. Or pause if necessary. Oh, okay. Now regarding the homework, remember the chapter 2 homework will not be due until way over here in October. All right. The thing is, I have to get a head start, right? Because we only have 16 weeks. I know it seems like a long time, but I have to get started with chapter 2 so that we can make the timeline. The chapter 2 homework is not due next week, none of it. But please keep up. It's to your benefit to keep up. So do what you can on chapter 2 next week. But of course, you're focusing on the chapter 1 homework. All right. Anything else? Anything else before we start? Feel free to chat. All right. Or if you want me to pause and talk, you can put that in chat. Pause and talk. All right. Okay. So let's get started.
Hi, everyone. In section 1.3, we looked at a gallery of basic graphs. Now in section 1.4, let's transform those graphs. And you're going to become a lot more powerful because you'll be able to graph a variety of transformed equations. Our first set of transformations will be translations or shifts. You see the details here in this box, but these shifts are best explained through examples. For example, let's take a look at the basic graph y equals the square root of x. That's from our gallery. That's that purple graph in the center here. We're going to consider various translations or shifts of that graph. And we're going to see the corresponding transformed equations. So let's start with the graph. This is Desmos Let's start with the graph of y equals SQRT, the square root of x. We get that hook, starting at the endpoint at the origin and extending through quadrant 1. Now, how do you graph y equals the square root of x all plus 2? What happens if I attach a plus 2 to the end here? We move the graph up 2 units. That makes sense because for every x value in the domain, notice the domain is the same. For every x value in the domain, we're going to get a y-coordinate that's 2 higher than the y-coordinate we got on the original red graph. So for example, at x equals 2, the y-coordinate on the blue graph is 2 units higher than the y-coordinate on the red graph, and so forth. Well, how do we shift a graph down by 2 units? Y equals the square root of x all minus 2. We go from the red graph down to the green graph. From the red graph to the green graph. We shift the graph down by 2 units. So these are vertical shifts or translations. They're the fairly obvious ones. To shift a graph up, you add a positive number at the very end here. To shift a graph down, you subtract a number. I'm assuming that you have the form y equals some expression in x. But what about the horizontal shifts? These are confusing for a couple of reasons. What if I want to take this red graph and shift it to the right by 2 units? Y equals the square root of x. I want to shift right. Actually, I'm not going to put plus 2. I'm going to put minus 2. And notice I'm doing it inside the radical. I'm substituting or replacing the x here with the x minus 2 over here. So you see we go from the red graph to the purple graph. Now, in fact, these are just horizontal shifts of each other, although it may not look like it because we tend to look at things kind of perpendicularly. But actually, if you look at things horizontally, there's always a 2-unit gap between the graphs horizontally. Likewise, to shift a graph to the left, it's y equals the square root of x. Now, to shift left, you might think it's minus 2. No, it's x plus 2. And again, it's inside the radical. You're doing a substitution, a replacement. And we go from the red graph here to the black graph over here. We're shifting left. So notice that the horizontal translations are harder for a couple of key reasons. Horizontal translations or shifts are harder for 2 key reasons. S's. First of all, it involves a substitution. A horizontal translation involves a substitution. You're substituting or replacing the x with x minus 2 in this case or x plus 2 in this case. Here you see the changes inside the radical. Second, 2 more S's. The signs surprise. Surprising signs. All these S's here. Because again, to shift right, you go from y equals root x to y equals root x minus 2, not x plus 2. The sign surprises you. Likewise, to shift left, you substitute the x with not x minus 2, but x plus 2. So these are 2 key reasons why horizontal translations are harder. They involve a substitution, you're substituting or replacing the x, and you have surprising signs. In general, horizontal transformations are harder if you have y as a function of x. Later on, we're going to see combining these various translations so we can shift horizontally and vertically. For example, we could do root x plus 2, y equals the square root of x plus 2, all plus 2. That takes the red graph and shifts it northwest, left and up. So that's how we do translations. Next, we're going to talk about issues of domain and range and graphs in general.
All right, any questions before we go on? Okay, we're moving things around. Any questions before we go on? All right, feel free to ask questions in chat. Oh, and by the way, closed captioning works. You know the ones I troubled closed captioning last time? It came a day late, so it took longer to close caption those last ones we had. They're now closed captioned, and these are too.
Hi, everyone. We can use a point plotting table such as this to help us with issues of domain and range, and also to get a sense of how these transformations work. So for example, consider the graph of y equals the square root of x. The domain for this function consists of the non-negative reals. For negative values of x, the function is not real or undefined. And we can do some basic point plotting. But what happens if we go from the graph of y equals root x to the graph of y equals root x all plus 2? Well, for each of the x values in the domain, notice that the y-coordinate increases by 2 units. We go here from 0 to 2, here from 1 to 3, and so forth. So for each value of x in the domain, the y-coordinate, the function value, goes up 2 units. And therefore, the graph goes up by 2 units. If we go from y equals root x to y equals root x all plus 2, notice that we go from 0, 0 to 0, 2. Notice we go here from 1, 1, 1, up to 1, 3, and so forth. Now what happens, so the graph moves up. Now what happens if we go from y equals root x to y equals the square root of the radicand x minus 2? Now notice that y equals 0 when x equals 2 over here on the new graph, but x equals 0 when y equals 0 when x equals 0 on the old graph. So basically what happens at x equals 2 on the new graph happened at x equals 0 on the old graph. Here I'm doing an analysis of X intercepts. Look at this warning over here. In case you're confused about horizontal shifts, right, consider the X intercepts of y equals root x versus y equals root x minus 2. We're asking what values for x will make y equal to 0. Here, it's when x equals 0. Here, it's when x equals 2. So the old graph had an x-intercept at 0, 0. The new graph has an x-intercept at 2, 0. Look over here. Y equals root x. At 0, 0, we have an x-intercept. At y equals the square root of the radicand, x minus 2, we have an intercept at 2, 0. The x-intercept moves right by 2 units, from the red graph to the purple graph. And in fact, that's true for all the points on the red graph as they move over to the purple graph. It may not look like a horizontal shift because we tend to look at things perpendicularly. We try to look at things perpendicularly, but we do get horizontal shifts here. So again, what happens at x equals 2 on the new graph happened at x equals 0 on the old graph. That kind of explains why from here to here, the graph shifts to the right by 2 units. It's kind of like daylight savings time where there's a 2-hour shift. Remember, 2 reasons why horizontal translations are confusing. The 2 S's. Remember, they involve substitution, and we have surprising signs. From the square root of x to the square root of the radicand, x minus 2, not plus 2, if you want to move to the right. Now, more frequently, we can use transformed graphs to figure out domains and ranges. So for example, when we go from y equals the square root of x to y equals the square root of x all plus 2, we're going from the red graph here to the blue graph over here, where we shift the graph up. What happens to the domain and the range? The domain, the x coordinates we pick up. The range, the y coordinates we pick up. What happens? Well, the domains stay the same because we pick up the same set of x coordinates on the red graph and the blue graph. The domain is the set of non-negative reals. It's still the set of non-negative reals, the domain. But the range, what happens to the range? The y coordinates all go up 2 units. 0 was the least real number in the range for the red graph, but 2 is the least real number in the range for the blue graph. So the range for the new blue graph starts at 2 and then goes off to infinity. Likewise, if we consider going from y equals root x to y equals root x minus 2, the radicand x minus 2, we're going from the red graph to the purple graph over here. What happens to the domain and the range? This time, the domain shifts up 2 units and the range stays the same. The domain shifts up 2 units and the range stays the same as for the original, the non-negative reals. So again, if you understand how a graph is transformed, that may be an easier way to figure out how the domain and the range may or may not be changing. Next up, reflections, more types of transformations.
Any questions before we go on? Any questions before we go on? All right. The challenge is working out the homework, right? Okay, let's go on.
Hi, everyone. How do we reflect graphs of functions? Let's look at y equals root x once again, the red graph. How do we reflect this graph about the x-axis so that the point 1, 1 goes to the point 1, negative 1, or the point 4, 2 goes to the point 4, negative 2? What equation will have a graph that goes to the green point here and the black graph, the black point over there? How about y equals the opposite of root x? So notice we're taking the opposite of the right-hand side. We're multiplying the entire right-hand side by negative 1. If you have more than one term, you'll need grouping symbols. So in order to reflect about the x-axis, you multiply the right-hand side by negative 1. How do you reflect about the y-axis? That involves the S word, substitution. We substitute x with its opposite. I'll do this in blue. Y equals root opposite x. We take the red graph and reflect it about the y-axis. We do that with a substitution. We substitute x with its opposite. And what if we were to apply both transformations? What if we reflect about both the x-axis and the y-axis? Y equals the opposite of the square root of opposite x. In orange. We say that we're reflecting about the origin. We get from the red graph to the orange graph by rotating 180 degrees about the origin. So to recap, to get from the graph of the original function to its reflection about the x-axis, you take the right-hand side and multiply it all by negative 1. You take the opposite of the right-hand side. I'm assuming you have the form y equals an expression in x. To reflect about the y-axis, you do a substitution. That S word, substitution. We substitute x with its opposite. And to reflect about the origin, you do both. and that corresponds to a 180-degree rotation about the origin. So from the original purple graph for y equals root x here, you can get these various other graphs from reflections about the x-axis, the y-axis, and the origin. And these principles apply, of course, not just to the square root function, but to other functions as well. Now, again, a point plotting table can help explain what's going on. Notice that if we go from the graph of y equals root x to the graph of y equals the opposite of root x, if we go from the red graph to the purple graph, what happens to the domain and the range? Well, the domain stays the same, the non-negative reals, but the range is flipped upside down. And we see that over here, from y equals root x to y equals opposite of root x. Domain stays the same, non-negative reals, but the range is flipped upside down. Remember that for the square root function, the domain and the range were both the non-negative reals. Now, going from y equals root x to y equals the opposite of root x, hey, check this out. The domain for root x was the non-negative reals. But what's the domain for the square root of the opposite of x? It's the non-positive reals. And that explains why when you go from the red graph to the blue graph over here, the domain is flipped around. The range stays the same, but the domain is flipped around. The domain consists of the set of non-positive reals, 0 and the negative real numbers. So the domain is flipped around, but the range stays the same as for the original, the non-negative reals. Once again, if you understand what the graphs look like, then that can help you figure out domain and range. Once again, and this will help you out a lot in calculus because people forget this, the square root of the opposite of x is defined as a real value for non-positive real values of x. A lot of people forget that. And that's because the domain looks like this. The non-positive reals looks like that. By the way, there is a connection with even and odd functions. The graph of an even function has a property that when you reflect it about the y-axis, you get itself. That's because you have symmetry about the y-axis. Likewise, the graph of an odd function is symmetric about the origin, because when you reflect the graph about the origin, you get the original graph. And that's explained algebraically here. Don't worry too much about that. No, the symmetries, the even symmetry here about the y-axis, the odd symmetry here about the origin, but you don't have to go too much into the details of the algebra here. So far, we've been dealing with rigid transformations, like we're dealing with a piece of wire and we don't have to warp it. What if we're allowed to warp the wire, squeezing it and stretching it? Then we get to non-rigid transformations next.
Okay, any questions before we go on? I know that whole thing about the square root of the opposite of x, that's confusing because remember, the square root of the opposite of -1 is the square root of 1, which is 1. Okay. Y equals square root of opposite x. So the point -1, 1 is on the graph because the opposite of -1 is +1. It's confusing. Confuses calculus students. Any questions? Any questions? Feel free to chat.
Hi, everyone. So far, we've been looking at rigid transformations, such as translations or shifts, reflections, and rotations, like about the origin. But now we're going to consider non-rigid transformations, which involve things like stretching and squeezing, where we can actually think of the graph as a wire that we're allowed to warp. We weren't allowed to warp the wire in these previous transformations. And we're actually going to look at an old friend of ours from trig. Y equals the sine of x. Our old friend, the sine wave. Now, what if we wanted to stretch this graph out vertically by a factor of 2. What number would we put where if we wanted to double the amplitude? We would want y equals 2 sine of x. We want a 2 out in front, and you can see that we're stretching from the red graph to the blue graph. We're doubling the amplitude, we're stretching vertically by a factor of 2. I could put a generic c in front, add a slider. If c equals 1, we're just matching the graph. It's in green. But as c increases, it moves away from the red graph. It's stretching vertically. If c is 1, then we're back to the red graph. Now, what if we wanted to shrink or squeeze the graph towards the x-axis? Then we could try something like y equals 1/2 x. I'll type it out. Y equals 1/2 x. Sorry, y equals 1/2 sine of x, I should say. Y equals 1/2 sine of x, that's in black. So from the red graph, from the red graph to the black graph, that's a vertical squeeze or shrink. Now, in green, we have y equals c sine of x. If c, the multiplier, goes from 1 down towards 0.7, 0.5, or 1/2, we see that we get vertical shrinking or squeezing. If c equals 0, we no longer have a sine wave. We just get the flat line for y equals 0. If c is negative, we start reflecting about the x-axis. We have that reflection about the x-axis. So in summary, the graph of y equals c times f of x is vertically stretched if c is greater than 1, like if c is 2, 3, pi, or 4. It's vertically squeezed or shrunk if c is strictly between 0 and 1, like if c is 1/2 or 0.7. By the way, if c is negative, then we perform the appropriate reflection. It's a reflection about the x-axis in this case. So vertical stretching and squeezing, it does all make sense. The multiplier corresponds to the type of stretching or squeezing that you have. Now over here, we're going to look at the square root function. In purple, we have y equals root x. If we look at y equals 2 root x in blue, notice that the purple graph is stretched vertically by a factor of 2. The red graph here is the graph of y equals 1/2 root x. Notice that if we go from the original purple graph to the red graph, then we get a vertical squeeze or shrink towards the x-axis. This makes sense because, for example, let's take the input x equals 1. On the purple graph, the square root of 1 is 1. The y-coordinate. Function values are y-coordinates. But if we put a 2 in front of the square root of x, the new y-coordinate is 2. It's doubled. If we put a 1/2 in front, the new y-coordinate is halved, down to 1/2. So vertical stretching and squeezing makes a lot of sense. But now horizontal stretching and squeezing might be counterintuitive. Again, in red, y equals sine of x. How do we do a horizontal squeeze towards the y-axis? How do we double? Actually, how do we cut the period in half? How do we cut the period in half? How do we squeeze towards the y-axis? Y equals sine of 2x. Put that in blue. So when we go from the red graph to the blue graph, we're squeezing in and we're cutting the period down to half. I hesitated there because, see, the number there is counterintuitive. Even though the period is half of what it was before, the period, by the way, is the horizontal width of a cycle, we actually put a 2 here, a number greater than 1. So if we have y equals sine of cx in general, that's now in blue. If c equals 1, we match with the red graph. If c increases, then we're squeezing the graph like a spring towards the They coincide. And then if C goes down to 0.8, 0.7, 1/2, it's actually getting stretched out. If C equals 0, it turns out we get Y equals 0, a flat line. If C is negative, then we get a reflection about the y-axis. Remember, f of opposite x leads to a reflection about the y-axis. So you can play with these sliders in Desmos. But again, it's a bit counterintuitive. Remember, y equals sine of 2x was squeezed in, not stretched out. It was squeezed in. If you want something stretched out, you want something like y equals sine of, let's say, 1/2 x. Going from the red graph to the purple graph, that's stretched out. Okay, so once again, horizontal transformations here, even the non-rigid ones, are harder. These horizontal transformations are harder. 2 reasons. Because they involve a substitution. Notice here that we're substituting the x here with a 2x over here for the blue graph and the 1/2 x over here for the purple graph. We substitute. You're changing that argument. You're changing inside the parentheses. You're substituting, replacing the x. And also, there's a surprise. But the surprise comes in the size of the number involved. So for example, going from y equals sine of x, you go to y equals sine of 2x. If you want to squeeze, it's not 1/2 x, it's 2x in there. Likewise, it's y equals sine of 1/2 x, not 2x, if you want to stretch. So this time, it's the size of the number that's counterintuitive. For a squeeze, you want a bigger positive number. So the graph of y equals f of cx, where the multipliers on the inside, basically it involves a substitution. You get a horizontal squeeze if c is greater than 1, and a horizontal stretch if c is like 1/2, if c is strictly between 0 and 1. Again, that's counterintuitive. And again, it involves a substitution, which people have trouble with. So the horizontal transformations are still harder. Now, you can think of this c as like an aging factor. I got this from Professor Peter Doyle. So for example, if you have y equals sine of 2x, that's aging twice as fast. If you have y equals sine of 3x, that's aging 3 times as fast. That's one way of looking at it. C is like an aging factor if it's positive. All right. So let's talk about horizontal stretching and squeezing. Y equals the square root of x. That's the guy in purple here, all right? Y equals the square root of x is in purple here. Now, if we want to squeeze, we might want something like y equals f of 4x or y equals root 4x. This here indicates a substitution. We're substituting x with 4x. It's inside that radical. You're substituting the radicand. And that leads to a horizontal squeeze towards the y-axis. Likewise, if you go from the purple graph to the red graph here, the red graph is the graph of y equals the square root of the radicand 1/4 x. Again, it's a substitution. This time it's a vertical stretch. So for example, for x equals 1, we get a y coordinate of 1 on the original purple graph. Now on the red graph out here, this is why horizontal transformations are harder, because they involve an idea of compensation. So when x equals 4, the new argument is 1, we have f of 1, and we get the same y coordinate as before. So if you plug in x equals 4 in for x here, it's the same as plugging in x equals 1 inside here. It's like a compensation almost. So what happens at x equals 4, that is when y equals 1, happens at x equals 1 here. Again, that's when y equals 1.
Let me pause here because I have an interesting point in chat. Let's go back to, so we have y equals sine of 2x, right? How do you reflect it about the x-axis? You put the negative sign in front, you get the blue graph. How do you reflect about the y-axis? Technically, you do this, But these two guys coincide actually, because it turns out these are equivalent. Sine's an odd function. These are in fact equivalent. So if you take the red graph, you get the same result whether you're reflecting about the x-axis or the y-axis. These are equivalent, by the way. That's not always true for all functions, but this is true for this guy.
Now, interestingly enough, the blue graph here, I'll erase all these. The blue graph over here is the same as the blue graph up here. And the red graph over here is the same as the red graph up there. And of course, the purple graphs are the same for y equals root x. Now, this is not true for all functions, but it's true for the basic square root function. It's true that every vertical stretch or shrink leads to a horizontal squeeze or stretch. So why is that? Y equals root 4x. How can I rewrite that? Well, I can rewrite root 4x as root 4 times root x. That's 2 root x, which is the same as this over here. The blue graph here is the same as the blue graph over here. Likewise, over here, for the red graph, root 1/4 x is the same as 1/2 root x. I can apply the square root factor by factor, which is the same as this guy over here. So it was very convenient here that for the basic square root graph, it's true that a vertical stretch leads to a horizontal squeeze, and a vertical shrink or squeeze leads to a horizontal stretch. But again, this is not true for all functions. It is true for the basic square root function. Again, play with Desmos, experiment. All right. Next up, sequences of transformations. What if we apply more than one of these?
All right, that's going to be very interesting. And this is interesting also. Any questions? Play with Desmos, or if you wanted me to do something, any questions? Any questions or requests? Sound like a DJ. All right. Let's keep chatting.
Hi, everyone. Let's apply a sequence of transformations. And this is related to the idea of compositions of functions later in section 1.6. Let's graph something like this. You have the power to do this without having to do too much point plotting. Graph y equals 2 minus the square root of the radicand x plus 3. Let's start at the beginning with a basic function and a basic graph that you know well. Where should we start? How about y equals the square root of x? What does that graph look like? That's our old friend, this hook. Now, different students might approach this in different ways, but how can we build up to this right-hand side here? Again, different students might take different approaches. Well, we could substitute x with x plus 3 and get that radicand. So we go from here to y equals root x plus 3. And when you substitute x with x plus 3, what do you do to this red graph? What happens to it? It's a substitution, so it's a horizontal translation. Which way? Remember, the sign is surprising. X plus 3, you might think right. No, you go left by 3 units. Remember, there are two ways in which horizontal translations are confusing. They involve a substitution and the sign surprises you. And then, what's the next step we can do? Symbolically. We can take the right-hand side and multiply by -1. And what impact does that have on the graph? It takes whatever graph we get here and then we reflect it about the x-axis. That's what happens when we multiply the right side by -1. Finally, we add 2. And some students might want to rewrite this so that the +2 is at the end. That's fine. It doesn't matter. But let's do that at the end. Add 2. Y equals 2, or you could put the 2 at the end. 2 minus root x plus 3. And what impact does adding 2 have to the graph we get from the green? We're going to go up 2 units. So here's what we want to do. We want to take this basic graph we know and love, y equals root x, our hook. We translate it or shift it left by 3 units. We take the result, reflect about the x-axis. We take that result and move it up 2 units. Let's do it. We start with this original Big Daddy graph, y equals root x. That's our basic hook. When we go to y equals root x plus 3, we're shifting left by 3 units. Don't worry about the intercepts for now. And then when we multiply the right side by -1, we reflect about the x-axis, and the graph now goes down from this point. Then when we add 2, we take this graph and move it up 2 units. Now, you don't have to worry about intercepts until the end, but the end point we have to care about anyway. We do care about what happens to the end point by the end, but we can actually trace its behavior. 0, 0, after we shift left by 3 units, that goes to -3, 0. Now, when we reflect about the x-axis, we call this a fixed point in the transformation. It doesn't change. It stays at -3, 0 when you reflect about the x-axis. And then when you move it up 2 units, it goes up to this point here. It's clear from the way that the axes are labeled that this is the point -3, 2, but it might be good to label it anyway. But at least do one or the other. Indicate the ordered pair or draw the graph and scale the axes in such a way, label the axes in such a way that we can tell where the endpoint is exactly. It's at the point -3, 2. Remember, you have to clearly indicate where any endpoints on a graph are. You must indicate where this endpoint is. As far as these intercepts go, I'll leave that to you, figuring out why the intercepts are where they are. I will make this comment. 2 minus root 3 is slightly positive. Remember that root 1 is 1. Root 2 is about 1.4. And root 3 over here, root 3 is about 1.7. Root 4 is 2. It's good to know some of these basic radical approximations. So root 3 is about 1.7. 2 minus root 3 is about 0.3. So this y-intercept is just slightly above the x-axis. That may be good to know because you might be curious to know whether the graph is going through quadrant 1 or quadrant 3. It turns out to go through quadrant 1 and not through quadrant 3. Though you may not know that until you do some point plotting or figure out where the intercepts are. If you plug in x equals 0, then you can figure out that the y-intercept is at 2 minus root 3, which turns out to be slightly positive. I'll leave it to you to find out why the x-intercept is at 1, 0. Okay, anyway, so we get this hook graph that starts at -3, 2, and that starts at -3, 2, and arcs downward. It extends on forever and ever. Again, different students might do it different ways, but you both have to end up with basically the same graph down here. So we've applied a sequence of transformations, a translation, a reflection, and another translation in order to get this final graph.
Oh, okay. So any questions before we go on? Any questions before we go on? Practice makes perfect, right? Work through the homework. Okay, any questions? All right.
Hi, everyone. Just now, we were given an equation, and we found the graph for that equation. We're now going to do the inverse problem. What do you think I mean by the inverse problem? I give you a graph, and you give me an equation. Finding an equation for a transformed graph. Now, to be fair, in chapter 1, I'm only going to give you graphs that can be obtained from one of our basic graphs through rigid transformations. However, in chapter 4, that's going to change. In chapter 4, in trigonometry, we're going to look at non-rigid transformations, like stretching and squeezing. But here in example 10, find an equation for the transformed basic graph below, where the transformations are all rigid. I'll give you 30 seconds. Start with which basic graph you'd start with, and then what transformations you would apply. Go. Here's another challenge. Another 30 seconds. Find another way of doing it. Go. Okay, I'm actually going to start with what's strategy 2 in my notes here. Well, first off, hey, what's the basic graph we want to start with? How about absolute value? So we're going to start with y equals the absolute value of x. Let's start there. Okay. And then, what are a couple of things we could do? Well, we could, okay, now here's the thing. I'm starting with an upward opening V. How do I get a downward opening V shape? I could start with a reflection. Reflect about the x-axis. And the corresponding equation would be y equals the opposite of the absolute value of x. Multiply the right-hand side there by -1. But wait, the corner point is currently at the origin. I need it to be at 0, -1. So let's lower this thing by 1 unit. And we should get this graph over here. Y equals the opposite of absolute x, all that, -1. And that should work. Let's verify this on Desmos. Y equals ABS for absolute value of x. Let's put a negative sign in front. Get the downward opening V, -1. And there you have it. All right, so that is that. So that's one way of doing it. A quick recap. Strategy 2, reflect, then drop. We go to y equals the opposite of absolute x, and we have y equals the opposite of absolute x -1. So that's one equation we can use for this graph. But there are other ways of writing the equation. there are different forms for the equation for this thing. Well, I'll pose this question. Now, remember, here we reflected about the x-axis and then dropped by 1 unit. If we were to switch the order here, would we get the same result? If we take the original graph, which was this up here, if we had taken this original Big Daddy graph up here, the absolute value graph, and if we had lowered it 1 unit and then reflected about the x-axis, will we get the same thing? Let's try it. If we lower it by 1 unit, we get y equals absolute x minus 1. Corner points at 0, -1, which is what we wanted at the end. But wait, if you try to reflect, if you try to multiply that entire right-hand side by a -1, uh-oh, this thing's too high. The y-intercept is at 0, 1, not at 0, -1. So this is wrong. It's not what we want. So the order can matter. The order can matter. We don't have commutativity here. The order can matter, especially if you're mixing up translations and reflections. Bear in mind, if you have a bunch of translations, you can apply them in any order. If you have a bunch of reflections, you can apply them in any order. If you have a bunch of rotations, you can apply them in any order. But if you start mixing types, you can get into trouble if you switch things or mix things up. All right, so what would be an appropriate way of doing it? Okay, what is one way that we can get the graph up here? What's a way of getting from the original Big Daddy absolute value of x graph to this transform graph over here? If we wanted to do a translation first and then a reflection, what would you do? You don't want to go down before you reflect. You want to go up before you reflect. Is that old saying, the taller they are, the harder they fall. Strategy 1, this is correct, this will work. Raise, then reflect. You actually want to add 1. Raise the V graph by 1 unit, so you have y equals absolute value of x plus 1, and then you reflect. You multiply all of the right-hand side, all of it, by -1. So notice I have grouping symbols here. I'll put that in red. You need the grouping symbols here. You're taking the opposite of all of that. And then you could distribute later on. So you could write an equation for this thing as y equals the opposite of absolute x plus 1. And what happens if you distribute? The -1, you get y equals the opposite of absolute x minus 1. And hey, that's the same equation we got as in strategy 2. Because we have equivalent equations. Y equals this is equivalent to y equals that. Remember that equivalent equations correspond to the same graph. So there are potentially different ways of getting the same graph. You can have different looking equations, although they are equivalent, but be careful of the order in which you do things, especially if you start mixing types. This over here did not work. Notice the equation here is not equivalent to what we had from before. Order can matter, especially when you mix different types of transformations. Next up, another way of looking at translations.
Okay, any questions before we go on? Any questions? Okay.
Hi, everyone.
Okay, wait, I have a few questions here. What if we wanted to reflect? What if we wanted to reflect graph? Okay, sorry. What if we wanted to reflect graph F2? What's F2? Let me. Okay, so if we reflect, well, yeah. If we reflect this, then we're getting the wrong one, right? And we don't have an equivalent equation here. Okay, I'm not sure which F2 you're referring to. Okay, F2 is just a second stage. Okay. Oh, okay. So yeah, I'm naming these things F1, F2 because it's a sequence of functions. So it's like, right, the original function is like the absolute value function, right? Well, when I want the graph for F, right? So I start with F1, the graph of my basic function. I transform to get F2, and then transform again to get F3 or just F. So technically, these are different functions. That's why I'm using subscripts. They're different functions, right? Any other questions before we go on? All right.
Now do translations using coordinate shifts. We're going to go back to an old example from section 0.13 on circles. And these techniques will work even for graphs that fail the VLT and situations where we don't have y as a function of x. So here we have the graph of x squared plus y squared equals 9. It's a circle of radius 3 centered at the origin. Now, in order to move the graph to the left by 2 units, meaning that the center also moves to the left by 2 units, we substitute or replace x with the quantity x plus 2, not x minus 2, x plus 2. So just like we've described before, the signs are surprising. We've seen that before for horizontal shifting. But now look at this. In order to move the graph up by 1 unit, in particular, in order to move the center up by 1 unit, we substitute or replace y with the quantity y minus 1, not y plus 1, y minus 1. So the signs are surprising for both horizontal and vertical shifting. The signs are surprising for both horizontal and vertical shifting. The signs are surprising in both the x group and the y group. Remember, the general form for the standard form for the equation of a circle is given by x minus h all squared plus y minus k all squared equals r squared, where hk is the center of the circle. Pretend that's a circle. Pretend that's the center. Here's hk, the center of the circle. All right. Again, to translate h units horizontally, if h is negative, you go left. To translate k units vertically, if k is negative, you go down. You substitute or replace x with x minus h and y with y minus k in parentheses or grouping symbols. That's the general principle I articulate in this box. And in fact, if you go to Desmos, if you consider x minus h all squared plus y minus k all squared equals 9. Let's add sliders for all, h and k. So if h is adjusted, we shift horizontally. If k is adjusted, we shift vertically. Hey, instead of 9, let's have r squared. Let's add the r slider. If you shift r, you change the radius. So together, by sliding around h and k and r, you can get all possible circles in the the xy plane. All possible circles in the xy plane. You can get by getting various values for r and h and k. R should be positive. But every circle in the xy plane will correspond to some values of r, h, and k. Keep on sliding. Keep on growing and shrinking. All possible circles in the xy plane. All right. Now, this is actually all consistent with what we've done earlier with functions. This is a generalization, but let's look at an example. Example 12. Let's look at this parabola, the graph of y equals x squared. Let's say that we want to
Wait, is there a drawing going on? Or I don't know.
Shift this parabola to the right by 2 units and then up by 1 unit. So to shift the graph to the right by 2 units, we substitute x, we replace x with a quantity x minus 2. Remember, it's not x plus 2, it's x minus 2. The sign is surprising. But by using the technique I just mentioned, if I want to shift the graph up by 1 unit, I substitute y with not y plus 1, but with y minus 1. I could put grouping symbols here, but that's not necessary. This is all alone out here. So by doing that, we get the corresponding parabola over here, shifted to the right by 2 units and up 1 unit. The vertex moves from 0, 0 to 2, 1. I guess I should have the horizontal shift in red. But how's this consistent with what we've seen earlier in the section? Well, like we said before, for a horizontal shift, the sign is surprising. Also, you substitute. You substitute x with the quantity x minus 2, not x plus 2, x minus 2. But now, look at this. If you add 1 to both sides of this equation up here, if you add 1 to both sides, then you just get y all alone on the left side, and you get this very normal looking plus 1 on the right. So when you add 1 to both sides of this equation to this equation, which looks more familiar to us from earlier in the section, basically we're going from a situation where the sign is surprising. Up here, the sign surprises vertically. The sign surprises vertically at first. But then over here, the sign is predictable. The sign is as expected. So up here, the sign surprises. To move up 1 unit, you substitute or replace y with y minus 1. But over here, after you add 1 to both sides, over here, well, if you want to move the graph here up by 1 unit, you attach a plus 1 to the right side. So that's why the vertical shifting makes sense. The signs are as expected. The horizontal shifts are still surprising because that's still a residue from what we did up here. We'll talk more about parabolas in section 2.1.
All right, any questions thus far? Any questions? Okay, any questions? So I want to do a brief thing before we took a break. I want to introduce 1.5 before we took a break, but we'll have one more short video before we take a break.
Hi, everyone. In section 1.5, we're going to discuss piecewise defined functions, or just piecewise functions, which are really useful in calculus. You often see these in the first chapter of a calculus book on issues of limits and continuity. A piecewise function is basically a function that has different rules for different subdomains, different x values. What's an early example of a piecewise defined function that we've seen before? I'll give you a hint. F of x equals x if x is non-negative, and it's the opposite of x if x is negative. What function did that? It was the absolute value function. So let f of x be the absolute value of x. What was the piecewise definition for the function? It was this. Like I said, the absolute value of x is x if x is non-negative. That is, if x is on this subdomain, bracket 0, comma, infinity, parenthesis. This is technically the subdomain. It's a set, a subset of the real number line. Now, informally, I might refer to this as a subdomain because that directly leads to that. but technically this is a subdomain. It's a set of x values, real values. So the absolute value of x, if x is in this set, that is if x is non-negative in value, but the absolute value of x is the opposite of x if x is negative in value, if x is in this subdomain. Again, I might just refer to this statement. And bear in mind, I could have had a bracket here because the absolute value of 0 is 0 in either case. So for example, how do we evaluate f of 3, or the absolute value of 3? Well, because 3 is a non-negative number, to calculate this, we would use the top rule, because x is non-negative. If x equals 3, x is non-negative, we apply the top rule. The absolute value of x is x. As far as x equals 3 is concerned, we totally ignore this bottom rule down here in the case where x equals 3. The absolute value of 3 is just 3, because the absolute value of x is just x in this case. Likewise, let's evaluate f of negative 3. I'll do this in blue. What's f of negative 3, or the absolute value of negative 3? Well, in that case, negative 3 is a negative number, which means that we apply the bottom rule. We apply the rule f of x, or the absolute value of x, is the opposite of x, because x is negative in value. We're in this subdomain. Negative 3 is a negative number. We're in this subdomain here. So we apply the rule f of x, or the absolute value of x, is the opposite of x. We don't care about this rule. We don't care about it whatsoever if x is negative 3. Well, the absolute value of negative 3 is going to be the opposite of negative 3. And the opposite of negative 3 is positive 3. So the absolute value of negative 3 is positive 3, according to the bottom rule. The top rule is irrelevant as far as negative 3 is concerned. So basically, the value for x, the value of the input or argument, that tells you which rule to apply, and you apply the rule in order to evaluate the function at that value of x. Incidentally, the domain is the union of the given subdomains. The union of these, though, is just R, the set of all real numbers. Okay. But if you have a number for which you don't have a rule, then that number is not in the domain of the overall function. Here, we do have a rule for every real value of x. But if you have a value of x for which there's no rule, it's out of the domain. Well, how do you graph this thing? Well, you want to graph y equals x if x is non-negative. So we get this ray over here, starting at the origin, going through quadrant 1. But if x is negative, we want y equals the opposite of x. We want to graph y equals the opposite of x. And that goes through quadrant 2. So we get the v-graph. But it's a v-graph that corresponds to two different rules for two different subdomains. We had a rule for this subdomain, and we had a rule for this subdomain. By the way, in calculus, you're going to say that the function is continuous at 0, because if you trace the graph of the function with a pencil in the vicinity of this point at x equals 0, you don't have to lift your pencil. That's an informal way of looking at continuity. You'll make it more formal in your calculus class. One reason why piecewise functions are interesting is that they're often discontinuous. They often lose continuity, especially when they switch rules. You often lose continuity when you switch rules. Then something like this might be happening. And that's when things get really interesting. That's why your first chapter in a calculus book will often focus on piecewise functions, because you might get jumps like this where you have discontinuity. Next up, how do you evaluate piecewise functions more generally?
Okay, but I want to do a preview of absolute value and show that connects together, that piecewise definition. So I have 8:16, so I think that's a good time for a break. I'm sure you would agree. So let's go ahead and take a break right now, and we'll start really with some new examples on piecewise functions back from the break. All right. So I'll see you at 6:20. Yeah, 6:27. Oh, no, not 6:20. 8:27. We're not going back in time. All right. So 8:27 back. Over here. Back at 8:27. Remember to mute if you're using the restroom, please. All right. I know I almost forgot something. All right.
Hi, everyone. Let's evaluate this piecewise function on various values of x. Example 1. Let the function f be defined by the following piecewise definition. F of x equals x squared if x is between -2 and 1. X could be -2. We have a weak inequality here. And f of x equals x plus 1 if x is between 1 and 2 inclusive, including the endpoints x equals 1 and x equals 2. So in other words, if x is in this subdomain, we square the input. If x is in this subdomain, what do we do with the input? We add 1 to it. So we have two different rules that do two different things depending on where x is. 4 questions for you. What are f of -1? Evaluate that. F of 1, f of 10, and what is the domain of this function? 4 questions for you. Evaluate these 3 function values and find the domain. I'll give you 30 seconds. Okay, let's begin. I'll tell you what a lot of students do. A lot of students look at the question, evaluate f of -1, please. All right, let's look at f of -1. Here's what a lot of students do. Oh, if I plug in -1 for x in the top rule, I get the square of -1, which is +1. If I plug -1 into the bottom rule, I get -1 plus 1, which is 0. So I guess f of -1 is both 1 and 0. Is that right? No. You may get no credit for this because you don't know what a function is. Take a look at this. If you claim this, you're claiming that the input value of -1 in the domain, it is in the domain, you're claiming that if we input -1 from the domain into this function, that it's spitting out a +1 and a 0 at the same time. A function is not allowed to do this. If you input a value from the domain, you cannot get 2 or more different outputs or y values. This cannot happen. So don't just take the input value and plug it into all the rules you see. You have to pick the rule and pick a final value. So which is it? Is it the 1 or the 0? Well, where's the -1? To evaluate f of -1, we use the top rule. Because to evaluate f of -1, we only care about what happens when x is -1. Which rule applies? Only the top rule. -1 satisfies that compound inequality up there. It does not satisfy the compound inequality down here. So -1 is in the top subdomain. Therefore, we apply the top rule. f of x or y equals x squared. What do we do with the input? We square it. The square of -1 is +1. The final answer is 1, not 0. The bottom rule has absolutely nothing to do with x equals -1. 0 has nothing to do with the answer. Again, if you put 1 and 0, you may well get no credit. You don't know what a function is. So f of -1 is 1, which means that the point -1, comma 1 lies on the graph. If x is -1, then y is +1. All right. Now, what about f of +1? I have to erase all this. Which subdomain and which rule will apply if x is +1? It's a close call this time, but if x is +1, the bottom subdomain applies. 1 is in the bottom subdomain because of the bar there. That's a weak inequality. See, over here we have a strict inequality. 1 is excluded from that subdomain up there. So x equals 1 only applies to the bottom subdomain, and therefore we only apply the bottom rule. What do we do to x equals 1? We add 1 to it. So to evaluate f of 1, we use the bottom rule because 1 is just barely in the subdomain on the bottom. So we use the rule f of x equals x plus 1. The x squared rule has nothing to do with this. F of 1 equals 1 plus 1. F of 1 turns out to be 2. Box that in, that's it. That's the value of f of 1. Now, what about f of 10? Well, there's no rule for x equals 10. Neither subdomain applies, neither rule applies. Therefore, 10 is not in the domain. F of 10 is undefined because we have no rule for it. And by the way, what is the domain? It's the closed interval from -2 to 2. Why? Because that's the union of these subdomains. The domain of f is the union of these two subdomains. So the lowest value in the domain, there is a lowest value, is -2. Sometimes there is no lowest value. You have a negative infinity deal going on, like for absolute value. But here, -2 is the least value in the domain. We walk on along. We just barely miss the 1, right? We miss the 1. But wait a minute. We pick up the 1 in the second subdomain. So there's a save. 1 is saved. 1 is in the overall domain. It's saved by the second subdomain. And then we walk along until we get 2. 2 is the greatest number in the domain. So we do get all the real numbers from -2 to +2, including the 1, which was especially risky because we changed rules at 1. But because of the bar there, because we had a weak inequality here, the 1 is still included in there. The domain is the union of these subdomains. Basically, the first subdomain is bracket -2, comma 1 parenthesis, union. Second subdomain is bracket 1, comma 2 bracket. The union of these subdomains is this over here, the overall domain. So f of -1 gives a real number, f of 1 gives a real number, but f of 10 does not. F of 3 does not. F of pi does not. F of -pi does not, because pi, -pi, they're not in the domain. Next up, how do we graph this function, this piecewise function?
Any questions? Because I know this section confuses people, but it's like dipping your feet in the cold water, right? I mean, dip your feet in, right? It's kind of shocking, but then you get used to it. Any questions? Any questions? It's a good thing you're here, as always, because I improve on the notes. I have a nice grid for how to graph these things with endpoints.
Hi, everyone. Let's evaluate this piecewise function on various values of x. Example 1. Let the function f be defined by the following piecewise definition. F of x equals x squared if x is between -2 and 1. X could be -2. We have a weak inequality here. And f of x equals x plus 1 if x is between 1 and 2 inclusive.
Did I
Not.
Yeah,
f of 3 does not.
I'm just
F of
repeating
pi
the
does
video.
not.
Okay.
F of negative pi
Oh.
does not, because pi, negative pi, they're not in the domain.
Okay, now we're going to the
Next
video.
up, how do we graph this function, this piecewise function? Hi, everyone. Let's graph this piecewise function. And remember that function values correspond to y coordinates. Now, this graph will have two pieces to it, although they could connect at x equals 1. We'll see. So we're going to look at the unrestricted graphs that correspond to these rules. We're going to see where the left endpoints are, and we're going to see where the right endpoints are, if any. Bear in mind that if we have something like this as a subdomain, there is no left endpoint. And if we have something like x is greater than 1, there is no right endpoint. But it does turn out that in this particular example, that both of these subdomains do each have two endpoints, and therefore the corresponding pieces of graphs, these two pieces here, will both have two endpoints, a left endpoint and a right endpoint. So we're going to fill in all four of these spaces. Again, sometimes you don't have a left endpoint, sometimes you don't have a right endpoint, but here we do get a left and a right endpoint for both pieces. Okay, so first off, let's consider the unrestricted graphs for these. How do you graph y equals x squared? Just a quick sketch. You don't have to be too accurate with this. Y equals x squared, that's going to be a parabola whose turning point, whose vertex, is at the origin. And how do you graph y equals x plus 1? You should know that from section 0.14 on lines. This was back in 1.3 on the gallery of graphs up here. This is from 1.3, the gallery of graphs. And here, this is from 0.14 on lines. Y equals x plus 1. Y equals mx plus b. That's going to be a slanted line of slope 1, whose y-intercept is at 0, 1. Again, just quick sketches. Now, on Desmos, we could graph y equals x squared and y equals x plus 1. And are we done? Is this the graph of our piecewise function? No. The answer is a big no. For one thing, the red and blue graphs together are going to fail what test massively? The VLT, or the vertical line test. If you offer this as your graph of f, this is way wrong because it's going to fail the vertical line test. That means that this wasn't a function. But we know it's a function. I told you it was a function. Not that you always believe what I tell you, but believe me when I say that we have a function here, f. So what we want is a piece of the red graph and a piece of the blue graph, and together they are going to pass the VLT. But what pieces do we want? Well, it would be helpful to know what the endpoints are for the two pieces. Let's look at the first rule here, y equals x squared, which is relevant for this subdomain up here. Technically, this is the subdomain. From -2 to 1, including the -2, but excluding the 1. Okay, so this subdomain has a left endpoint at -2 and a right endpoint at 1. So this piece of the graph, if we just graph this, we'll have an endpoint at x equals -2, a left endpoint, and an endpoint at x equals 1, a right endpoint. So for the, and I'll write down the rules here. This is for y equals, well, this is for f of x equals x squared. And this is for f of x equals x plus 1. And I'll circle them for emphasis.
Yeah, I had to cut the video kind of short here because of technical difficulties. Any questions before we go on? I'm starting with the unrestricted graphs. That's a nice place to start, but we're not done yet. The endpoints, a lot of details in the endpoints. Any questions so far? Any questions so far? All right, going on.
So now the left endpoint for the first subdomain is at x equals -2. The right endpoint for the first subdomain is at x equals 1. The left endpoint is at x equals -2. The right endpoint is at x equals 1. So then, what are the corresponding outputs for this rule here? Well, here, x gets squared by the f function to get the output. F squares the input to get the output. So for x equals -2, what's y going to be? Y is going to be the square of -2, or +4. Which means that the corresponding left endpoint will be the point -2, 4. So that's going to be the left endpoint of this piece of the graph. Now, will it be included or excluded from the graph? Well, x equals -2 is in the subdomain for this first rule. Because of that bar there, that weak inequality, this point will be included. Put that in green. So the left endpoint will be included on the graph. The right endpoint of the subdomain is at x equals 1. So we're going to plug in 1 for x. Now hold on. Some of you might be saying, 1 is not technically in the subdomain here. Good point, literally, good point. But here's the thing. Let's plug in x equals 1 anyway. So the corresponding right endpoint will have y coordinate 1 squared, which will be 1. The corresponding right endpoint will then be 1, 1. But now wait a minute. X equals 1, look at that parenthesis, look at the lack of a bar there. We have a strict inequality. X equals 1 is technically not in the subdomain up here, this first subdomain. So the right endpoint, for now, is excluded from this first piece of the graph. The first subdomain just barely misses x equals 1. 1, 1, that right endpoint is excluded. Now you might be wondering, well, wait a minute. By what right do we have to plug in x equals 1 in the first place to even get the y coordinate of the endpoint? Well, here's the deal. It's an idea of a limit in calculus. If you plug in x equals 0.9, x equals 0.99, x equals 0.999, well, the function values, the y coordinates will be the squares of those. As x approaches 1, we're approaching 1 squared. As x approaches 1 from the left, from inside this subdomain, as x approaches 1 from the left, going along that piece, we're approaching 1 squared, or 1, the y coordinate here. It's a limit idea. On this parabola, here's the point 1, 1. Now, for now, the point 1, 1 is not on the graph, but as we walk along this piece of the parabola we're picking up, we're approaching that point. We're approaching that point, even though this point for now is not on the graph. So for now, it's excluded. Now, it remains to be seen whether the second piece here will pick up the point 1, 1. Sometimes the second piece will pick up the point 1, 1, and we actually have continuity at x equals 1. But let's see. Do we get continuity or not? We'll see next time.
All right. Any questions before we go on? Any questions before we go on?
Hi, everyone. So do we get continuity at x equals?
Okay, well, I want to ask, any questions? A lot going on here at the endpoints, right? So like I said, people have a hard time getting used to this, but then you get the knack of it. Any questions? Any questions?
One or not. All right, let's take a look at this second rule on the second subdomain. The second subdomain is the closed interval from 1 to 2. The left endpoint of the subdomain is at x equals 1. The right endpoint is at x equals 2. Bear in mind, these don't always match. Here they do. Okay, let's see if we can get continuity here. Let's plug in these two endpoint values into this rule, x plus 1. So y equals 1 plus 1. That's going to be not 1, but 2, which means that the corresponding point is going to be at 1, 2. That's going to be the left endpoint for the second piece. Now, 1, 2 is a different point from 1, 1. There's no way that we're going to have continuity. There's going to be a jump here. Because of the bar there, we have a weak inequality. X equals 1 is included as part of this subdomain. The point 1, 2 is included as part of the second piece of the graph. Now, what about the right endpoint of the subdomain, x equals 2? Let's find the right endpoint for this second piece of the graph. Plug in 2 into x. Y equals 2 plus 1, or 3, which means that the corresponding point on this piece will be 2, 3. But is it included or excluded? Because of the bar there, it's a weak inequality. X equals 2 is part of the subdomain. Included. The point 2, 3 is included. So both endpoints are included on the second piece of the graph. Well, now what? Well, we've now answered the questions. What pieces of these graphs do we want? What piece of the red graph, what piece of the blue graph do we want? And we can now graph the overall graph, which looks like this. And by the way, it's great that you're seeing this video because this grid is actually not a part of my notes. I describe it in my notes, but the grid helps a lot. It's a good thing you're watching this video. Here's the graph of the function. So the first piece is part of a parabola with vertex at the origin, although you could point plot also. The left endpoint is at -2, 4 up here. That's included as part of that first piece, the left endpoint. The right endpoint at 1, 1, however, is excluded. Because the left endpoint is included, I'm putting a nice solid dot at -2, 4. Because the right endpoint at 1, 1 is excluded, I'm putting an open hollow circle at the right endpoint. By the way, we call this an open endpoint, not a hole. It's not a hole because there are no points immediately to the right of it. It's an open endpoint at the right end of this first piece. That's the piece of the red parabola that we want. Now, what about this piece of line, this line segment that we see here? Well, I want a piece of this slanted line that's going from 1, 2 to 2, 3, and I want to include both endpoints. Well, we're going from 1, 2 to 2, 3 along the slanted line segment, and we're including both endpoints. Solid filled in dots at the endpoints. That barbell. Again, notice that 1, 2, and 1, 1 are different points. There's a jump here. In fact, we say in calculus that there's a jump discontinuity at x equals 1. In order to get from this graph to the other, you have to jump up onto this piece. Also in calculus, we would say that the function, as x approaches 1 from the left, approaches 1 in function value or y-coordinate. That's the y-coordinate of that endpoint. And from the right, the limit as x approaches 1 from the right is 2. The function values approach 2. So again, and I talk more about limits later on in the notes, but as x approaches 1, the left-hand limit, as you come in from the left-hand limit is 1. The y-coordinates approach 1 from the left. The right-hand limit is 2, because the y-coordinates or function values approach 2 from the right. Now again, the reason why we were able to get the point 1, 1 as the right endpoint for this piece is that, hey, 0.9, comma 0.9 squared, that's a point in this graph. 0.99, comma 0.99 squared, that's a point in this graph. This piece of the graph, if you walk along this piece of the graph, you're approaching 1, comma 1, even though you're not allowed to reach it. In fact, this idea of a limit, it doesn't care whether the function values actually exist or not. It doesn't matter if you have open endpoints here or not. The right-hand limit would still be 2, whether it was an open endpoint or closed endpoint. By the way, if I had made this a solid filled-in circle, a solid filled-in dot, if I had thought that the right endpoint were included on the first piece, how would I know that I was wrong? This graph would just barely fail what test? The vertical line test, right there at x equals 1, which means that it cannot be the case that both these endpoints are included. It's possible that both might be excluded. A function allows for this, an open endpoint at 1, comma 2, but you cannot have a point at 1, 1, and 1, 2, both included on the graph, if y is a function of x. This, however, is okay. So remember, your final graph has to pass the VLT, the vertical line test. Don't just turn this in as a final answer. This massively fails the VLT, the red and blue graph together. However, notice here, this graph does pass the VLT. And notice, this is the entire graph. There are no arrows going off anywhere off towards infinity or whatever. This is the entire graph. I'll erase these. There's no arrow stuff going on as this stands. This is the entire graph with finite arc length. The entire graph. There's nothing beyond what you see here. What you see is what you get. That's the entire graph. We'll talk more about piecewise functions later on.
All right, any questions so far? This is one of the trickier topics for people to pick up on. If this is your first time taking pre-calculus, you may not have seen this before, except maybe absolute value. Even that, seeing absolute value and the definition. Piecewise functions are pretty new for people. Any questions? Any questions? Do those homework problems. Any questions? Okay, by the way, the fun videos are coming up. You're gonna like these videos, but I have another video and then I have a game show. So watch this next one, then I have a game show.
Hi everyone, how would you graph the following piecewise function? Graph y equals f of x if f of x equals x plus 3 if x is not equal to 3, but f of x equals 7 if x equals 3. I'll give you 20 seconds to ponder this. Okay, the domain is all real numbers. How do you graph y equals x plus 3? Well, that's just going to be a slanted line, slope 1, with y-intercept at 0, 3. You should know that from section 0.14. But wait a minute. For now, as we graph the first piece, we're not allowed to have a point with x-coordinate 3, because 3 is not in a subdomain for this rule. So for now, we have to put a hole at x equals 3. Now on the line, the hole is at 3, 6. If you were to just graph y equals x plus 3, there's normally a point on the graph at 3 comma 6. But because we're excluding x equals 3, we're not allowed to have a point at 3 comma 6 on the graph. We have a hole for now. Now, wait a minute. What does the second rule do? Y equals 7 if x equals 3. In other words, the point 3 comma 7 is on the graph. 3 comma 7 is on the graph. That's like a moon. The graph looks like, well, let's reiterate. We graph the line y equals x plus 3, except we leave a hole at the point 3 comma 6. Since 3 was deleted from the subdomain, the bottom rule defines f of 3 to be 7. That's what it basically says. F of 3 equals 7. That's what the bottom rule says. That's why 3 comma 7 is on the graph, which means the graph of the piecewise function looks like that. I hope you're able to give yourself an A+. So in calculus, we say that there is a removable discontinuity at x equals 3, in the sense that you can get a continuous function if you just take this moon point and move it down and fill in that hole, spackle in that hole, if you redefine f of 3 to be 6. A removable discontinuity is a fancy way of saying hole. That's what you call a hole in calculus. We have a removable discontinuity.
Oh, okay. So, you know the line y equals x plus 3? Normally, 3, 6 is on it. Because when x equals 3, y equals 6. But because 3 is not in the domain of the first guy, we have to omit that point, see? Any questions? We have to omit the point because we're not allowing x to be 3 anymore. Up in the first subdomain. Let me go here. Oh, it's on 1.5, sorry. Yeah. X cannot be 3 in the first subdomain. Okay, so we have a hole.
Continuity at x equals 3, the point 3 comma 6 is a hole. There are points to the left on the graph, points to the right on the graph, but in itself is not on the graph. In fact, we would have a hole there whether the point 3, 7 were there or not. Now, I don't really like the term removable discontinuity because you're not allowed to redefine f of 3 just because you feel like it. There's no rule by which we're allowed to move this point down into that hole and spackle in that hole. So I don't think the term removable discontinuity is appropriate. I think it's a misnomer, but in calculus, you use it. It's a standard term in calculus. We have a removable discontinuity at x equals 3. There's a hole at 3 comma 6, whether there's a point at 3, 7 or not. But there is a moon up there. Notice the graph does pass the VLT. We have a function here. Now, we just said that f of 3 was 7. The function value at 3, the y-coordinate at x equals 3, was y equals 7. That's why the point 3,7 is on the graph. So f of 3 equals 7. That's a pre-calculus question. What is f of 3? What's the function value at 3? It is 7. Oh, wait. Doesn't 6 have some relevance, though? Yeah, but that's a calculus idea. That's a limit. So in pre-calculus, we say that f of 3 equals 7. But in calculus, we can say that the limit of f of x as x approaches 3 is 6. In other words, as x approaches 3, f of x, the function value, the y-coordinate, approaches 6. It's like Romeo and Juliet. Romeo is running along this graph from the left, approaching x equals 3 from the left. Juliet approaches x equals 3 from the right. They're both approaching the point 3,6, so the limit value is 6, whether or not they meet or not. So we're not being very romantic. We don't care if they meet or not. What matters is that they're approaching each other. So the limit of the function as x approaches 3 is 6, even though the point 3,6 itself is on the graph, the point 3,7 is. So once again, and make sure you understand this distinction in calculus, the function value at 3 is 7, but the limit value as x approaches 3 is 6. the function value is 7 because 3, 7 is the point on the graph, but the limit value is 6 because Romeo and Juliet are approaching y equals 6, even though they never meet. Aw. Next, we're going to talk about a graph that kind of looks piecewise, but it has its own applications. Next time.
All right, and now time for a game show. Before we get to the game show, which leads on to this new function, any questions? Any questions regarding like graphing this thing? I know there's some questions there, right? We're graphing y equals x plus 3. That was the slanted line, but x was not allowed to be 3 on that line. So we're no longer allowed to plot the point 36 as part of that line. We have to omit it, pluck it out. In fact, at x equals 3, y equals 7, the point 37 is on the graph, so we get the moon there. The graph of that function looks like this. A line with this removed point, we add a point up there. Any questions before we go on to the game show?
So when we find the x coordinate for the first one, we use the bottom.
Wait, are you talking about this one? This example?
Yeah. So x plus 3, we use x equals 3 from the bottom part.
Oh, okay. Now the idea is, how do we graph y equals x plus 3? Because bear in mind, for every value of x that's not 3, we're graphing y equals x plus 3. So, well, how do you just graph y equals x plus 3? Assume for now that the domain is all reals. Well, it's your slanted line, right? Y equals mx plus b, where m is 1, and m is 1. I'll type it out. Where the slope m is 1, and b equals 3 indicates the y-intercept, right? So if I were to ask you to graph y equals x plus 3 back in section 0.14, when we were graphing lines, you would graph this line with the point at 3, 6. It would just be a normal point on the line. But the problem is, hey, wait a minute. This linear rule only applies if x is not 3. So based on the first rule alone, the first piece here, you're not allowed to have a point with x equals 3 because 3 is not in the subdomain. I have to pluck out that point. I have to pluck it out, omit the point 3, 6, pluck it out. And then the second rule here says, and bear in mind, I don't even need this to have a function, but it turns out the domain is all reals. I want a rule for f of 3. I'm saying here that f of 3 is going to be 7. I'll type it out. Okay, from here we're getting that f of 3 equals 7 from this bottom rule. When x equals 3, the function value, the y-coordinate, is 7. That means the point 3, 7 lies on the graph. Right. So, of course, the second rule has basically nothing to do with the first rule. Remember, overall, I got to pass the VLT. And this does. Any further questions about how this looks? Any further questions? Okay, any further questions? Okay, well, you can continue to chat. Before I talk about the greatest integer or floor function, I call this the Price is Right function, and here's why. There's an item up for bids or a big package up for bids. The winner is the person who makes the closest bid to the actual price of the items without doing what, folks? Without going over. If you don't know the game show, I'm going to pause this.
Hi, everyone. Let's discuss the greatest integer or floor function. Basically, this function rounds down. Here's f of x equals the greatest integer of x or the floor of x. The result, the output, is the greatest integer that is not greater than x. I think of this as the Price is Right function after the old game show. If x is the actual price of the item up for bids, then the output of this function, the function value, is the best integer bid you can make that's closest to the actual price of the item up for bids without going over the price. Think rounding down. So for example, try to figure out what these values are. The greatest integer, or the floor of, 2.9 for 3, and for negative 1.1. All right. Now, it's the same function, so we get the same outputs. The greatest integer and 4, they mean the same thing. So if you round down 2.9, you get 2. You don't round off, you round down. I know it rounds off to 3, but you round down to 2. If you round down 3, well, you get 3 itself. If you round down any integer, you get the integer itself. Now, this is where a lot of people mess up. If you round down negative 1.1, remember, you're rounding down, not rounding off. This is a lot like the 2.9, actually. If you round down negative 1.1, you go all the way down to negative 2. There's a way of looking at this. So let's say that x is the number that you're taking the floor of. The result, the output of the function, is the greatest integer, the integer furthest to the right, that is not to the right of x itself. It does not go over. It's the integer that's furthest to the right, is the greatest integer without going over, without going to the right of x. So for example, for 2.9, even though 3 is a lot closer than 2, the 3 goes over. So you don't want the 3. The 3 goes over, you do not want the 3, you want the 2. It's the greatest integer to the left of 2.9. Or more precisely, it's the greatest integer that is not to the right of 2.9. Because look at our next example. What if x is 3 itself? Well, the greatest integer that does not go over is 3 itself. The greatest integer, or floor, of any integer is itself. Now here's the tricky one. Negative 1.1. Here's negative 2. Here's negative 1. The greatest integer without going over. The negative 1 goes over. We don't want them. The negative 2 is the greatest integer, is the integer furthest to the right that does not go over. Negative 1 is the next integer and it goes over. So negative 1.1 rounds down to negative 2. This function is often used in computer science applications, like in programming. There's also a ceiling function where you round up, but I won't discuss that. The graph of this is very interesting. It's a staircase graph. It's a staircase graph with a lot of jump discontinuities. In fact, infinitely many jump discontinuities. But this function and this graph is often studied in the first chapter of a calculus book because you talk about ideas of limits and continuity. We have infinitely many jump discontinuities at the integers, the integer values of x. So for example, at x equals 2, the left-hand limit is 1, but the right-hand limit is 2. The fact that the left-hand and right-hand limits mismatch, they exist, but they mismatch, it means there's a jump discontinuity at x equals 2. So for example, if the item up for bids is actually $2 or $2.10 or $2.25 or $2.50, $2.50 or $2.99, what is your best integer bid if you're playing the Price is Right? If you round down 2 or 2.1 or 2.99, you get 2. Which explains why you get this flat piece here. If the item up for bids is worth $2, if you round down 2, you get 2. Your best bid is $2. If the item is worth $2.10, $2.20, even $2.99, your best bid is still $2. If you round down 2.99, it's still 2. Now, if you round down 3, you get 3 itself, so you jump up to here. So again, you often see this graph in the first chapter of a calculus book, Issues of Limits and Continuity. But keep this kind of staircase graph in mind. Now, the remainder of these notes are optional. If you're serious about previewing calculus, you should skim over these notes. I introduce ideas of limits and continuity formally in this part. So for example, if you want to know the limit of a function as x approaches 2 from the left, for example, that's the notation, you can consider what happens at x equals 1.9, 1.99, and so forth. Same thing for right-hand limits. You can look at 2.01, 2.001, and so forth. Lots of arrows you can draw. So I talk about limits, like the idea that as x approaches 1 from the left, the function values, the x squared values, approach 1 from below. That was the function we talked about earlier, where you can plug in x equals 0.9, x equals 0.99. The function rule x squared applied, and the y coordinates approached 1, even though the 0.11 was never achieved by that piece of parabola itself. There's an open endpoint there. So the left-hand limit as x approaches 1 is 1, but the 0.11 is not on the graph. When do you have continuity? Well, it's when, let's say at x equals 0, right? Why is there continuity at x equals 0 for the absolute value function? Because the left-hand limit exists, it's 0. The right-hand limit exists, it's 0. And the left-hand limit equals the right-hand limit. They both happen to equal 0. And the function value is 0. The limit value equals the function value. That's when you have continuity. Continuity means basically that the limit value exists and equals the function value, which also exists. In this case, the limit value and the function value is 0. There are 3 types of discontinuities you talk about in calculus: removable discontinuities, or holes, like in this previous example we talked about, whether there's a moon there or not. Jump discontinuities, like in these graphs. And infinite discontinuities, like for example, for y equals 1 over x. That's really messed up. There's no way of fixing that. Next up, more ways of combining functions.
So before we do that, I have some videos about a key application of piecewise functions. Any questions before that? Any questions? Piecewise functions, get lots of practice on the homework. Where do we see piecewise functions? Economics, marginal tax rates. Okay, now in this example, it looks like we've had severe deflation, right? Because look at these dollar amounts, they're very low, but this is a textbook problem, right? But here's an example, a textbook example of different marginal tax rates for different income brackets. For example, Bernie Sanders and AOC, they proposed like a 70% marginal tax rate on very, very high income brackets. That margin though, not the average tax rate, on the margin. All right, let's talk about this. Or let's John talk about this. Oh, Hi
everyone. In section 1.5, a piecewise function was one function that could have different function rules for different subdomains. But how can we combine functions, multiple functions? Well, we can add, subtract, multiply, and divide them, as you might expect. For example, let f and g be functions. The function f plus g has a rule, f plus g of x, that can be defined as f of x plus g of x. You have similar rules for f minus g, f times g, and f over g. The domain of f plus g, for example, is the overlap or intersection of the domain of f and the domain of g. In order to be a legal input for f plus g, you have to be a legal input for both f and g. You have a similar domain rule for the others, except that with f over g, there's an additional restriction. The denominator cannot be 0. So for example, let's say that we want to consider f where f of x equals x squared, and g where g of x equals x cubed. Well, you could consider a table for the function f plus g. Basically, you add the function values, you add the y coordinates to get the y coordinates you see in brown, And you might be able to consider point plotting. Some of you may have this skill, others may not. It's not really crucial to have this skill, but it's nice to have. Can you believe that basically the blue function, f, plus the red function, g, gives the brown function, f plus g? You're thinking in terms of adding y coordinates. Basically, blue plus red equals brown. If you can't really see that, don't worry about it. Here's an example where we're subtracting functions. Let f of x equal 4x, and let g of x equal x plus 1 over x. How do we get a rule for f minus g of x? Well, you can break this down as f of x minus g of x. F of x is 4x. G of x is x plus 1 over x, but remember, if you're subtracting something with more than one term, you must put grouping symbols. Or go ahead and distribute. At this point here, we can distribute 4x minus 1 over x. A lot of people miss that minus sign. 4x minus x is 3x, and we can say that the function rule for f minus g is given by f minus g applied to x is given by 3x minus 1 over x on the domain of the function f minus g. But what is the domain of f minus g? Well, over here, what's the domain of f? The implied domain of f is all reals. It's a polynomial. But what about g of x? It's all reals except what number? It's all reals except 0, because we have to avoid a 0 denominator. So all real values of x, all real numbers, will be legal inputs for f and g except for 0. He's no good. He's the only one who's no good. So the domain of f minus g is a set of all real numbers except 0. And there are various ways of writing that down. Set difference form, set builder form, interval form. We skip 0. Again, you can multiply functions, but here, let's consider dividing functions. And the domain question is more complicated. Let f of x equal 1, and let g of x equal x over x minus 2 on their implied domains. Find the rule for f over g of x, and find the domain of the f over g function. Let's write out the rule for f over g of x. It's given by f of x over g of x. F of x is 1. G of x is x over x minus 2. Let's simplify this expression. What is the reciprocal of x over x minus 2? It is x minus 2 over x. And what is the domain? What is the domain? Well, clearly from here, in this final fraction, it must be the case that x cannot be 0. Otherwise, we're trying to divide by 0. In particular, notice that x equals 0 makes g of x equal to 0, the thing we're dividing by over here. So x equals 0 would produce a 0 denominator over here. X equals 0 makes g of x equal to 0. And we cannot divide by 0 down here. But wait a minute. Look over here. 1 over the fraction x over x minus 2. We have a problem if we're dividing by 2 down here. So x cannot be 2 either. But that restriction is hidden when you take the reciprocal. If you look at this final expression, it's not clear that x cannot be 2. But since 2 is illegal,
I just said you can't have x equals 2. You can't divide by 0.
It's also illegal over here. In particular, note that 2 is not in the domain of the g function. 2 is not in the domain of the g function. It makes the denominator 0. So x cannot be 2 because x equals 2 makes g of x undefined. In other words, 2 is not in the domain of G. Bottom line, you have a problem if you're divided by 0. Up here, 2 is not in the domain of G because x equals 2 makes you try to divide by 0. But we cannot have the fraction itself be 0. X cannot be 0 either because we're trying to divide by g of x. So both 0 and 2 are illegal. This is a hidden restriction. We have to write this down. The domain of f over g in set difference form, and also in set builder form, graphical form, and interval form. We skip 0 and 2. Now, in addition to f plus g and f minus g, we could also consider things like 3f plus 4g, or pi g, or 0, or this thing. These are examples of linear combinations of f and g. Functions of the form number times f plus number times f. Number times g. And it turns out that the domain rule is the same as for f plus g in particular. The domain of 3f plus 4g, for example, is the overlap, is the intersection of the domain of f and the domain of g. The only legal inputs for this guy are the legal inputs for this and for this. We like linear combinations of functions. There are nice calculus rules for these also. Next up, a more creative way of combining functions, composition.
Okay, so we talked about adding, subtracting, multiplying, and dividing functions. Remember when subtracting, use grouping symbols. That's key. Also domain, right? Keep notions of hidden restrictions, right? Don't divide by 0. That's a big issue. Don't divide by 0. Any questions before we get to composition? And we're down to the last couple videos. Any questions? All right.
Hi, everyone. A more sophisticated way to combine functions is to compose them, which is when you apply functions in sequence, like we did in section 1.4 on transformations, when we applied a translation, then a reflection, then a translation. Compositions of functions.
Actually, you know what? I'll play my Family Guy video at this point before I forget. All right.
Here's a good example of that. Let's say you input a number into your calculator, a value for x, and then you press a function button on your calculator, a g button on your calculator. The result is going to be g of x, the resulting number on your display. And then let's say you press the f button on your calculator, a function button, which takes this as the input. So the output for the g function now becomes the input for the f function. The output, the final output, will then be f of g of x. Now consider merging these two calculator buttons together as a single button or function, f circle g. A calculator button that first applies the g function and then the f function. We go right to left in the same way that we go inside out with parentheses. So remember, the function f circle g applies g first and then f. You press the g button first, take the output, and then press the f button. So let f and g be functions. The composite function f circle g is defined by f circle g of x equals f of g of x. Now the domain is a bit freaky looking, but don't worry, I won't be pushing you too hard on this. What are the legal values of x that will get us a real output out here? The set of all x in the reals such that x is in the domain of g, so it's a legal input to g. It's a legal input to the first button, and the resulting output, g of x, is a legal input for the f button. So the domain consists of legal inputs to g that yield outputs that are legal inputs to f. The set of all x in the real such that x is in the domain of g and the outputs g of x are in the domain of f. Again, it's rather complicated, and I won't be pushing you on that. Now, order might matter. F circle G may or may not be the same function as G circle F. Composition is not a commutative operation. For example, think about reflections and translations back in section 1.4. In the exercises, you'll do some examples. Here's an example of composition. Let f of u equal 1 over u, and this does turn out to be easier when you have u as your independent variable here. It's less confusing. Although in principle, you could have f of x equals 1 over x. There's nothing wrong with that, except that it can end up being confusing. In any case, f here is the reciprocal function on the implied domain. G of x equals root x minus 1. All right, find f circle G of x and the domain. Bear in mind, though, I won't be pushing you on that too hard. All right, so f circle G of x. So again, remember, f of u is 1 over u. G of x is root x minus 1. F circle G of x is f of G of x. G of x is root x minus 1. What does f do to root x minus 1? Well, what does f do to any legal input? Takes its what? Takes its reciprocal. So we take the reciprocal of root x minus 1, we get 1 over root x minus 1. Another way of looking at this, this is f of u, where the result is 1 over u, and you substitute in, this is u, g of x is u. You substitute this in for u. We want f of u, where u is root x minus 1. What is f of u? It's 1 over u. What was u? It was root x minus 1. You substitute or plug in. Now, I'm not going to push you too hard on the domain issue in the context of composite functions, but this would be or would have been legal on exams. If I were to say h of x equals 1 over root x minus 1, then we could treat this as a straight domain problem. When does this yield real results? If and only if x minus 1 is positive, that is, when x is greater than 1. And it does turn out that's the only restriction on the domain, even in the composite setting. There are no other hidden restrictions. So here's the domain of f circle G in set builder form, graphical form, and interval form. However, sometimes there are hidden domain restrictions, sometimes kind of complicated ones. But our focus here will be, again, on how to construct the rule for a composite function. Let f of x equal 1 over x squared minus 7, and g of x equal the square root of x minus 3. Find f circle G of x, that's our key concern. And also we'll discuss the domain of f circle G. All right. Now, first of all, it might actually be to your benefit if you rewrite this rule as f of u equals 1 over u squared minus 7. Because some people are going to find it weird to plug in something in x in for x. That's weird for some people. F circle G of x is f of G of x. G of x is the square root of x minus 3. I'll put that in red. The square root of x minus 3, that goes in here. And what is f of root x minus 3? Well, substitute this in for u here. This is u, the input, the argument to f. You put that in for u here. Or if you just leave in terms of f of x, you plug this in for x, but that seems kind of weird. In any case, you get 1 over this thing, blah, squared, minus 7. 1 over the u guy, root x minus 3, that's squared, minus 7. The square of the square root of x minus 3 is x minus 3. As long as this is non-negative, the x minus 3, I'll mention that later. I will note that though, x minus 3 cannot be negative. That was the case way up here. But see, when we square the radical, we're going to hide the restriction. So we have 1 over x minus 3, all minus 7. We get 1 over x minus 10. Now, it should be evident from the final expression that x cannot be 10. But there was a hidden restriction. The radicand here cannot be negative, and this is equivalent to x being at least 3. So that's a hidden restriction. So here's the composite function rule. That's my key concern, but the domain is more complicated. X cannot be 10, but also x has to be at least 3. It's easiest to see graphically. X has to be at least 3, but we have to skip over the 10. In interval form, you can get the interval form from the graph. But again, I would not ask this on an exam because you're talking about the domain of a composite function framed as a composite function. I think that's too complicated. Even books have a hard time explaining it. Next up, something you're going to have to do a lot of in calculus. How do you decompose a composite function? I give you a big ugly function or a function rule. How do you break it down into bite-sized pieces that calculus can attack?
Okay, this is the last video. It's a short one.
Hi, everyone. Let's decompose composite functions. This is like breaking up a monopoly. Let's say you're given a function, f circle g, let's say, whose rule is given by f circle g of x equals the square root of 3x plus 1. How can we break up this function into bite-sized, smaller, easier pieces that calculus can more easily chew on? So, x is the input. How can we construct nicer functions, calculator buttons, g and f, such that when you press them in order, the final output is the square root of 3x plus 1? Now, be fair. Literally, be fair. Imagine that this is a group work project where g and f are on the same group. X is the work that's coming in, and this is your final output. Well, and I know many groups work like this, we don't want g to take in the work x and just spit out x. We don't want g of x to just be x. We don't want g to just be the identity function. So neither f nor g is allowed to be the identity function on homework or exams because this guy's just too lazy. G is just passing on the work for f to do, and f's doing all the work. You're just renaming x as u, basically. That's illegal. So we have to break up this function or function rule more creatively. So if x is the incoming work, what can g do? So what can g of x be? What can g of x be? I'll give you a hint. We often let g of x be an inside guy, an inside piece that we would like to replace with u, that we'd like to substitute with u. I think many of us would agree that we would like to replace the 3x plus 1 with u. And that's often our choice for the inner function rule, g of x. Let g of x be 3x plus 1. And then, if 3x plus 1 is the output for g, what does the f function have to do? What does the f button have to do to get us this as the final output? Take the what of the input, the 3x plus 1. Take the square root. So the f function should be the square root function. F of u, let's say, should be the square root of u. So to recap, a natural breakdown would be for the inner function rule, g of x, to be 3x plus 1, and for the outer function, f, to be given by f of u equals the square root of u. So g of x spits out the radicand, and f takes the square root. Although there are infinitely many possible ways to get to here. For example, maybe g is just a little bit lazier. Maybe g takes in x and just triples it. and does not add the 1, and then passes that work on to f, f has to add the 1 to the input u, and then take the square root. So f of u is given by the square root of u minus, the square root of u plus 1. Still, the end result is the square root of 3x plus 1. One way to check this is to do a substitution. If you substitute 3x into u, you get the square root of 3x plus 1. This works out. Just like over here, if you plug in 3x plus 1 in for u here, the radicand, you get the square root of 3x plus 1. Either way, it works. Here, in our first solution, g did two things. It multiplied the input x by 3 and also added 1 to the result. It got the whole radicand, basically, and f took the square root of the result. Here, g just triples the result. Sorry, g just triples the input. Okay, and then f takes the output, the result, adds 1, takes the square root. Either way, it's fine. In the last part of my 1.6 notes, I talk about applications to word problems. I encourage you to read this as a preview to calculus, but I won't push you on this. Until then.
Wow, thank you for your persistence. That was quite a trek. All right, quite a trek. 1.4, 1.5, 1.6. Any question? I'll take questions. Okay, we're still recording. Let me know if you want me to stop recording. Any questions? Any questions? Homework for chapter 1 due Friday of next week. And please be patient. While I'm still doing these new videos, grading's taking forever. All right, questions? Thank you. I'll stop the recording now then. Stop the recording.